और आज का लेक्चर स्टार्ट करने से पहले हम थोड़ा पिछले क्लास की चीजों को एक बार रिकॉल करते हैं कि जैसा कि हमने किसी भी रोलिंग बॉडी के लिए एक्सेलरेशन हमने फाइंड किया था, लाइक इफ द बॉडी वाज रोलिंग by some force F, then the acceleration of center of mass, we have calculated this force divided by mass upon 1 plus I by mr square. And in another case, if the object is rolling over an inclined plane, for inclined plane, the center of mass having acceleration equals to g sin theta upon 1 plus I upon mr square. And this I was definitely we were taking about its center of mass. Whatever structure we had, we have always calculated this I with respect to the center of mass. Now, see this question. This question I used to put in my notebook, in my notes every year when I teach, and this question was asked in IIT JEE 2019, which we have done in the last class. So you can see, as I repeatedly speak to you, that everything in the examination will be related to my notebook. So if you see, the structure may be different. It may be hollow sphere, solid sphere, hollow cylinder, solid cylinder, and it will be rolling like this. And we are asked to calculate the acceleration of the center of mass. Definitely, acceleration depends on what? Applied force, which is in this case mg sin theta. But simultaneously, since it is rolling, so rolling has what? Some alpha also because of torque. So this alpha contributes in the acceleration of the center of mass, linear acceleration of the center of mass. In that regard, this is the perfect formula which we have derived in the last class, and we have calculated the acceleration of center of mass for several bodies. And in the examination, what will happen? This theta will be given. So every time you will know the value of sin theta. Many a times this question has been asked directly for sphere, for cylinder. Theta was given, mass was given, radius was given. So in that case, you calculate the acceleration of center of mass, and you will get the answer in the numerical form. Okay. So please remember these things. Now, as we have discussed in the last 2-3 classes, very important concepts were there. That's why if you focus on my speed, then I have gone very smoothly, very slowly, because the concept was very, very crucial. We need to understand these concepts very carefully. That's why we have done very less thing in 40 minutes, but we have done these things in a very good way. Okay. So definitely, if we see the discussions which we have already seen in the previous classes, so mainly we were asked to find what? The acceleration of center of mass, angular acceleration, or acceleration of this object, this body, which I have taken here, like this plank, yeah, acceleration. And every time main thing which were asked was acceleration of center of mass. Then we have seen the importance of this word sufficiently rough. It means what? This disk is going to perform a pure rolling motion over this plan. So what we have seen for condition of pure rolling motion, like bodies in contact, the acceleration at the point of contact on both of the body having tangential component equal to the each other. Like if we see the first point in this disk, it has an acceleration because of this force, because this force will provide some acceleration to the center of mass, and because of having alpha, because of having torque, there is also one more acceleration. And if you see, the object is rotating in clockwise direction, so this point will have alpha times r in the backward direction. One more acceleration in case of having alpha to the body in this circular object. Another acceleration we can have is omega square times r. And if we see the second body, which is the plank, it has acceleration in the forward direction. So as we have seen, the tangential acceleration of point of contact should be equal. So first equation we make, this A equals to the acceleration of second object should be equals to the acceleration of center of mass plus alpha, sorry, minus alpha times r. Why minus? Because alpha r is in the opposite direction. This is the relation number 1. Then we have seen one more relation, the net force F minus this friction force, whichever will be acting because the surface is sufficiently rough. So a friction need to be considered here. This friction will have, net force will have relation like mass into the acceleration of center of mass. Then we have seen the rotational analysis, the torque about center of mass. If I apply the torque about center of mass, then the torque due to this capital F force will be 0, and the torque due to the friction will be F times R. Okay, and this is equals to what? I alpha. What is the I of the disk? Mr square by 2 times alpha. So this relation, third relation, and one more relation, there is a relation between alpha and acceleration of center of mass, which I have written here in the first relation. So wherever we need to replace this alpha by ACM, we have to use this relation. And one last relation is that if you just say that there is a friction here F, then this friction has reaction over this plank F, and we know that the body which are in contact moves with the reaction, like friction force will be equals to the mass of the plank into the acceleration of the plank. One more relation we can have. So main thing is that we should have sufficient number of equations as per the number of unknowns need to be calculated. So every time you have to see these things, you should be able to write the relations. Now we are ending up with the rolling motion. That's why I was just summarizing that what we do in the case of pure rolling motion. Now I would like to move to the calculation of kinetic energy of a rigid body performing complex motion. So put the heading kinetic energy of a rigid body, kinetic energy of a rigid body performing complex या combined rotational and translational motion. So if we see the kinetic energy of a rigid body performing both kind of motion, we can write the situations like this. The kinetic energy of a rigid body will have contribution in the kinetic energy because of rotation. So I can write the rotational kinetic energy. So rotational kinetic energy is written in the center of mass frame, half I about center of mass, moment of inertia about center of mass into omega square, because the motion is combined rotational and translational. So it will also have a translational kinetic energy, which is half m, and the velocity of center of mass square. So this will be the relation which we are going to use whenever the kinetic energy of any rigid body needs to be calculated. I would like to write here this half moment of inertia about center of mass square. This is called what? The rotational kinetic energy in center of mass frame, or simply you can write the rotational rotational kinetic energy of the rigid body. You can write the rotational kinetic energy of the rigid body. Now, one more relation, half m velocity of center of mass square, and this is called what? Translational kinetic energy of the rigid body. Translational kinetic energy of the rigid body. So we can see the calculation of rigid body will be done in two different parts, and for total kinetic energy we'll have to add the individual one. Now I would like to have one question here for calculating the kinetic energy of this kind of rigid body. Like if I have a solid sphere, if I have a solid sphere of mass m and radius r, which is purely rolling, pure rolling, we have to find first part the total kinetic energy, the total kinetic energy, and the second part we have to calculate is ratio of is the ratio of rotational rotational kinetic energy and the translational kinetic energy. These questions are very common question from the rotational motion. So you have to calculate these two things, and the surface on which this solid sphere is lying is sufficiently rough. Sufficiently rough, we understand that in case of sufficiently rough situation, we can consider that the body is going to perform the pure rolling motion, and it is given that its center of mass has velocity v naught. Now I give you 1 minute to solve this question, so I'll be waiting for your answer. क्या है इसमें sufficiently rough है, इसका मतलब प्योर रोलिंग मोशन होगा. प्योर रोलिंग मोशन में अगर मैं इस वन पॉइंट की बात करूं तो इस वी नॉट की वजह से कुछ ओमेगा डेवलप हो जाएगा. इस फर्स्ट पॉइंट की मैं बात करूं, इसके पास एक वेलोसिटी वी नॉट राइट डायरेक्शन में और ओमेगा नॉट टाइम्स आर या ओमेगा टाइम्स आर, द वेलोसिटी विल बी इन लेफ्टवर्ड डायरेक्शन बिकॉज ऑफ रोटेशन. और इस सेकेंड पॉइंट को अगर देखो तो इसकी वेलोसिटी क्या है दूसरे पॉइंट की, 0. इनको इक्वल करेंगे तो वी नॉट माइनस ओमेगा आर क्या हो जाता है, 0. इसका मतलब जहां कहीं भी आपको ओमेगा की आवश्यकता पड़ेगी, यू कैन सिंपली यूज वी नॉट बाय आर. So this is the first relation which we are going to use. Pankaj and Vipin, your answers are absolutely correct. Now see कि मुझे क्या लिखना है, टोटल काइनेटिक एनर्जी. तो टोटल काइनेटिक एनर्जी मैं लिख सकता हूं हाफ मोमेंट ऑफ इनर्शिया अबाउट सेंटर ऑफ मास इंटू ओमेगा स्क्वायर प्लस क्या लिख सकते हैं, हाफ मास ऑफ द बॉडी इंटू वेलोसिटी ऑफ सेंटर ऑफ मास का स्क्वायर. बहुत अच्छे. विपिन, आपका आंसर उल्टा है. पंकज, योर आंसर इज करेक्ट. नाउ सी, if we write the moment of inertia of a solid sphere about its center of mass, it is 2 by 5 mr square, and omega has value v by r, v naught by r square, plus half mass of the sphere v naught square. If we solve these things, we are going to get the m v naught square by 5 plus m v naught square by 2. The answer is 7 by 10 times m v naught square. This is the total kinetic energy. This is the first part. Now if we see the second part, the ratio of total rotational kinetic energy. What we have written, rotational kinetic energy, which is m v naught square by 5, and the translational kinetic energy is m v naught square by 2. So the answer is 2 by 5. You can see a very good objective questions can be framed from this. Now we have one more question. I would like to draw the question first. Ring is there. Please write the question. A ring is there, and the ring having mass m and radius r. And this ring is placed on a surface which is again sufficiently rough. साहिल, आपके आंसर क्यों नहीं आ रहे हैं? आयुष, आप, राजीव, कोई आंसर नहीं कर रहा है. तुम लोग लेक्चर ऑन करके भाग तो नहीं जाते हो? sufficiently rough. ये सिंपली मैं ऐसा करके शॉर्ट में लिख देता हूँ. दिस सरफेस इज सफिशिएंटली रफ, और इसके सेंटर की वेलोसिटी है v नॉट, और इसका खुद का मास है लाइक आई टेक द मास ऑफ द रिंग. यहाँ पर मैंने कैपिटल M लिखा है, तो इसको भी स्मॉल m मान लो. मास ऑफ द रिंग इज स्मॉल m, and two objects are attached to this ring. One having mass m, another one also having mass m. Okay, and because of having sufficiently rough surface, it will be performing a pure rolling motion. You have to find the kinetic energy of the system. What is the kinetic energy of the system? Okay, and answer me the solution. I will wait for 1 more minute. क्या है कि यहाँ पर तीन ऑब्जेक्ट, एक ये जो कि वी नॉट स्पीड से आगे बढ़ रहा है और डेफिनेटली कुछ ओमेगा रहा होगा इसमें, प्लस दूसरा मास है, मैं इसको ये वाला मास मान लेता हूँ, इसको फर्स्ट मान लेते हैं, इसको सेकंड मान लेते हैं। तो इस फर्स्ट वाले के पास, ये तो एक पॉइंट ऑब्जेक्ट है, तो इसके पास सिर्फ और सिर्फ ट्रांसलेशनल वेलोसिटी होगी। अब देखो ये आगे बढ़ रहा है, मैं इसको ओमेगा ऐसा मान लूं, तो इसके पास वेलोसिटी कितनी होगी, वी नॉट प्लस ओमेगा टाइम्स आर। ओके, then the second body will have only, not only, it has one v naught in the rightward direction and omega naught r in the downward direction. अब आपको इन सबके इंडिविजुअल मास, इंडिविजुअल क्या काइनेटिक एनर्जी लिख करके इनके ऐड करने, देखता हूं मैं क्या आंसर आते हैं। यहाँ पर क्या करना होगा, एक रिलेशन तो हम डायरेक्टली यूज कर सकते हैं कि v नॉट इज इक्वल्स टू ओमेगा टाइम्स आर। मतलब ये जो ओमेगा आर मैं लिख रहा हूँ, इसको लिख सकता हूँ वी नॉट, तो फर्स्ट वाले ऑब्जेक्ट की वेलोसिटी आ जाएगी 2v0, और ये भी v नॉट है, इसकी स्पीड कितनी आ जाएगी, क्योंकि काइनेटिक एनर्जी किसी बॉडी का लिखने के लिए अपने को सिर्फ उसकी स्पीड की आवश्यकता होती है, हाफ एम वी स्क्वायर से हम लिखते हैं काइनेटिक एनर्जी। सो दिस वी नॉट एंड दिस वी नॉट हैज रिजल्टेंट अंडर रूट 2 वी नॉट। Now I will simply write the kinetic energy of all the objects. So the kinetic energy of system will be the kinetic energy of the ring, which is half m v naught square, plus kinetic energy, rotational kinetic energy of the ring, which is half moment of inertia of the ring. We know that it is mr square, and then v naught by r naught because omega square. Okay, plus the kinetic energy of the first body, which is 2 v naught square, plus the kinetic energy of the second ball which is attached is half m root 2 v naught square. So if we add all these values, the first value is going to be half, both are half m v naught square, because r square and r square will get cancelled. So first section has kinetic energy half m v naught square, sorry m v naught square, and second has 2 m v naught square, and the third has m v naught square. So the kinetic energy here we are getting is 4 m v naught square for this system. Quite easily done. Now the Pankaj and Vipin, both of you got different answer and wrong answer. So please be careful. Questions are very easy. If you see what we have to do, we have actually written the individual kinetic energy of this ring and this ball, and again for this ball, and nothing new we have written. But we know that this ring is actually what? Rolling. So we have to write the rotational kinetic energy along with the translational kinetic energy. So if you see, this ring is placed on a fixed surface. So it has velocity v naught in this direction, omega r in this direction, and the point of contact has velocity, should have velocity same. So if we use this relation, then definitely we are getting v naught equals to omega naught times r. This analysis becomes different if the surface on which the ring is placed also starts what? Moving, also moves, like in the case in which we have we have taken the flank. Okay, सर बॉल का मोमेंट ऑफ इनर्शिया कंसीडर नहीं करेंगे, क्यों करेंगे, बॉल के पास तो इंस्टेंट काइनेटिक एनर्जी है ना, v नॉट प्लस ओमेगा आर, तो इसके लिए मैं क्यों करने जाऊंगा मोमेंट ऑफ इनर्शिया कंसीडर। ये तो रोटेट नहीं हो रहा है ना, इस इंस्टेंट पर सिस्टम की काइनेटिक एनर्जी बतानी है, आप देख लो। ओके, एक दूसरा मेथड भी हो सकता है, आप इस मेथड को खुद से ट्राई कर लेना, जो आप कह रहे हो वो भी आंसर आ जाएगा। हमने किया है ऐसे क्वेश्चन को सॉल्व when we were defining the kinetic energy in case of rigid body or system of particles in case of rotational motion. Now I have one more question. You have to find out the kinetic energy of the rod, and I will draw the diagram. This is a rod which has its acceleration, its velocity of center of mass VCM, and it has omega. So how will you write the kinetic energy? Definitely this is not clamped. This rod is not clamped. Clamped means it is not fixed. If an object is not fixed, that means we can say that means the rotation is about the rotation is about center of mass. So what is the kinetic energy of the rod? It will be half moment of inertia about what? Center of mass omega square plus half mass of the rod and velocity of center of mass square. So nothing new. If the velocity will be given, we can calculate these things. The important thing is that we should consider the moment of inertia ml square by 12. Whatever omega will be given, we will be just utilizing those values here in the relation. So according to the given value of velocity of center of mass, okay, or angular velocity of the rod, and the specification of the rod like mass will be given 1 kg 2 kg, and the length of the rod will also be given. So accordingly we have to solve the question. Now I would like to give you one more question which we have already done in our basic classes. See, this is a rod, and if this rod is fixed with the ceiling, okay, and this rod has mass m, length l, and it starts revolving with omega, so the center of mass will have some velocity. It is like velocity of center of mass. You have to write the kinetic energy of the rod. What we are going to do, we will write half ml square by 3 because it is now fixed about one of its end. So the moment of inertia about this point will be ml square by 3. Then we can write the half m velocity of center of mass square. So this will be the answer. So as we see, this question can also be solved simply if you see what is the velocity of center of mass. If we have calculated this thing many a times, okay, this is omega L by 2. So at this place you can put this omega L by 2. हमने क्या किया यहाँ पर हमने रोटेशनल काइनेटिक एनर्जी लिखा हाफ आई ओमेगा स्क्वायर, और इस रॉड का इसी इंस्टेंट पर ट्रांसलेशनल काइनेटिक एनर्जी को लिखा। लेकिन आप इसी क्वेश्चन को अगर सेकंड मेथड से, जो हमारा फेमस मेथड था, उससे सॉल्व करोगे, काइनेटिक एनर्जी हमने क्या लिखा है, हाफ आई मोमेंट ऑफ इनर्शिया अबाउट एक्सिस ऑफ रोटेशन, half into moment of inertia about axis of rotation into omega square. Oh, sorry. इन दिस सॉल्यूशन आई हैव मेड अ मिस्टेक, क्योंकि मैं यहाँ पर अलग अलग मोशन कंसिडर कर रहा हूँ। तो ये क्या होता है, दिस मोमेंट ऑफ इनर्शिया इज, देखते हैं कि हमने यहाँ पर क्या लिखा है। वी हैव रिटेन द काइनेटिक एनर्जी। देखिए क्या लिखा है, मोमेंट ऑफ इनर्शिया अबाउट सेंटर ऑफ मास। लेकिन हम अगर डायरेक्ट इसको सॉल्व करना चाहें, यहाँ पर हमें ml²/12 लिखना होगा, लेकिन इसे डायरेक्ट सॉल्व करना चाहोगे तो आप देखना आज पलट के कि हमने टोटल काइनेटिक एनर्जी जब कैलकुलेट किया है तो यहाँ पर मोमेंट ऑफ इनर्शिया अबाउट सेंटर ऑफ मास रखा है। तो आप यहाँ से भी कैलकुलेट करके देखना। अब लिखेंगे ml²/3 क्योंकि इसको एक एंड पर फिक्स कर दिया है, और आप मैच करना, दोनों के आंसर सेम आएंगे। नाउ if we see the next heading, work energy theorem in rigid body, theorem in rigid body performing complex rotational and translational motion, performing CRTM। तो आप तो देखो कॉन्सेप्ट तो सारा सेम ही है। इसका मैं फर्स्ट पॉइंट लिखता हूं, इन केस ऑफ प्योर रोलिंग, इन केस ऑफ प्योर रोलिंग, if friction comes, if friction comes into picture, अगर प्योर रोलिंग के केस में फ्रिक्शन की बात हम करेंगे तो ये हमेशा स्टैटिक होता है, ये हमने नोट किया है। इट इज ऑलवेज स्टैटिक इन नेचर, वी हैव रिटन it is always static in nature. Thus net work done by this rolling friction, जब भी रोलिंग फ्रिक्शन की बात होगी तो नेट वर्क डन जो है रोलिंग फ्रिक्शन की वजह से इज ऑलवेज जीरो, is always zero as work done by static friction on the system is zero। स्टैटिक फ्रिक्शन की वजह से वर्क डन क्या हो जाता है सिस्टम पर, जीरो। देखिए हमारे लेक्चर का टाइम कंप्लीट हो रहा है। वर्क डन बाय ऑल द फोर्सेस इज इक्वल्स टू टोटल काइनेटिक एनर्जी फाइनल माइनस टोटल काइनेटिक एनर्जी इनिशियल। तो आप लोग अच्छे से इसको पढ़ के आना। नेट वर्क डन, यहाँ पे वर्क एनर्जी थ्योरम में हमने क्या किया, नेट वर्क डन इज इक्वल्स टू चेंज इन काइनेटिक एनर्जी ऑफ द रिजिड बॉडी। सो सी यू गाइस टुमारो, थैंक यू सो मच, टेक केयर ऑल ऑफ यू।